We've done this enough now. Y'all are all familiar with it, but I cannot assign the exploration. So click on the reading. It takes you to the chapter. Click on Explore More Resources. We're in the Explore tab. We're looking for the exploration. So click on Explore More Resources up top here. And once you get to that page, scroll all the way down to the bottom. And the last thing you see will be the Exploration Plate Tectonics Interaction. Click on that. It should open up in a new tab or a new window. I think new tab for y'all. And let's see what they got here. Let's do this exploration. So let's just explore a little bit here and see what they want from us at the beginning. So they have different boundaries. They have convergent in red, divergent in yellow, transform in blue. Do they tell us to do anything? Can't click on anything here. So let's go to interactions. And they have three different types that we can choose from here. We can do continental, continental, oceanic, oceanic, or oceanic, continental. And we have convergence, divergence, and strike slip. So let's start with what they already have selected here. Continental, continental, convergence. Let's see what happens. When two continental plates smash together, what you get slowly, if it happens correctly, is going to be a mountain range. So as they collide, there's nowhere for them to go but up. They will not push down into the surface. And so you have this nice mountain range that is formed here from continental-continental collisions. The feature that is marked by the dotted lines is going to be what? It's not normal faults. Normal faults are where they're pulling apart. Fold and thrust mountains. Yeah, I don't know why I didn't read that the first time. Fold and thrust mountains is going to be it. This is obviously a mountain range, so the mountains answer is going to be correct. Good job. Thank you. Reset this. Let's go to oceanic convergence. They're going to come together. One of your oceanic plates is going to be pulled down underneath the other one. You're going to get a little bit of a trench, and you'll get some volcanoes showing up out in the ocean, similar to like the islands of Japan. So now that that's done, proceed. Identify the feature. That is going to be the trench. So you can see there's this deep canyon out in the ocean right in between the two plates. That's going to be your deep ocean trench, similar to the Marianas Trench. Next, where are we at here? Reset. Let's do oceanic continental. You're going to have the same thing, but this time the volcanoes are going to be on land. Instead of volcanoes being out in the ocean, they're going to come up and be just offshore. So think like Mount St. Helens in Washington. That's the kind of volcanoes that you're looking at there. So proceed. Active volcanoes is what's circled there in the red lines. Now let's go to divergence.
You have to go to like continental.
Oh, yeah. So divergence, continental. They're going to start to split apart. Eventually, if your valley gets big enough, it will connect to the ocean, and you will have ocean water fill this in, and it will become a new ocean basin. They're not showing the water come in, but essentially that's what's going to eventually happen. What do they want us to do here? We need to circle these parts. These are going to be normal faults. So when I have extension, I'm going to have things breaking down. That's going to be normal faults happening there. Good job. Reset. Is there an oceanic one? Yes. So your oceanic plate starts to pull apart. Pretty much the same thing, but this time it's underwater. What's right here in the middle? This is going to be your mid-ocean ridge. So right in the middle of the ocean, mid-ocean, I have this little ridge where my volcanoes are being formed, my new plates being formed. Submit, continue, reset. There is no oceanic continental for that. Perfect. Go to strike slip. Continental strike slip, similar to the San Andreas Fault in California. So they're just going to slide right next to each other. Notice there's nothing going up, nothing going down, no volcanoes or anything, just earthquakes. So the feature there is going to be a fault line. So strike slip fault system should be the correct one there. Reset. They have oceanic strike slip. Pretty much going to be the exact same thing that happens. It just happens underwater. And still going to be a strike slip fault. And let's see. Is there an oceanic continental one? Yes, there is. Again, exact same thing that happens. They're just going to slide right next to each other. And it's going to be a strike slip fault. Wonderful. So now we have all that done. We can go to the tracker. And they have everything at the tracker, I believe. Looks like maybe we're missing a couple things. But let's see what they have as far as questions are concerned. So what do we have? 10 questions. No second page. Wonderful. Perfect. So let's just read the overview and see what it says. Overview. Continents and ocean floor move as parts of huge slabs of lithosphere known as tectonic plates. The plates converge and diverge and slide past each other, moving at a rate of a few centimeters per year. So just real quick, everybody, these things move at a few centimeters a year, which is very small. Centimeters, very small, just a couple a year. The rate they compare this to is about the rate that your fingernails grow. So imagine if you didn't cut your fingernails for a whole year, how long they would be. That would be the distance that the plates move roughly in a year, depending on what plate you're talking about. And yes, people with long fingernails, like the world record holder fingernails, are just really gross. Sorry if you aspire to be that person, but we're all a little weirded out by you. And you're like brown curly fingernails that are like 3 feet long.
You think it hurt?
Probably. I don't know. It's weird. They have to like keep them in bags and like walk around like this so they don't break.
It's like, listen, pick it up. It's like, bend down.
Yeah.
Up if they did that.
Yeah, it's weird. It's real weird. Let's just acknowledge that. All right. So question number 1. How are volcanoes and earthquakes related to plate tectonics? So the earthquakes part is easy. How are earthquakes related to plate tectonics? Yes, so the movement of tectonic plates as they slide past each other or interact in really any way is going to build up the pressure used to create earthquakes. So plate tectonic interactions or movements cause earthquakes. How are volcanoes associated with plate tectonics? Yeah, so when the plates move, they cause earthquakes. So plate movement causes earthquakes. What about plates causes volcanoes? Huh? No, well, not necessarily divergence. It's actually convergence. But no, you're right. Divergence does happen to you have volcanoes that come up. But those are all small and they're in the middle of the ocean. So the bigger ones, what happens? Actually, let me go back because I got a little image up here.
Is that called a hot spot?
No, it's not the hotspot one. Look at this. Hold on. Convergence. And it was oceanic. Let's do oceanic continental. What is happening for these volcanoes to form? What's going on here? Yes. So that's the other part that's related to volcanoes. When I have plate that gets pushed down and melted, that creates volcanoes. So plates moving creates earthquakes. Plates being pushed down in the earth and getting melted creates volcanoes. So that's how volcanoes and earthquakes are associated with plate tectonics. Plates moving causes earthquakes. Plates being pushed down and melting causes volcanoes. Number 2, scientists examine the composition of the volcanic rocks that erupt from volcanoes. Explain what information about Earth's interior they can gather from this. So we're looking at the composition of volcanic rocks. So we can tell what type of minerals are in there. So we know what type of minerals are inside the rocks. We can tell what type of rocks were melted to create that lava. Because lava didn't just like appear. It had to come from somewhere. It had to be melted from some sort of rock. So we can tell what kind of rocks got melted to create that. Earth's interior, can you gather from that? So if we know the composition, we can also know what temperature it melted at. So melting temperature. We can know what kind of gases are in there. So what kind of atmosphere maybe you have. I don't know, it's not really atmosphere, but what kind of gases are melted in there? What else do we have? Not from volcanoes, explain what information about Earth's interior they can gather from this. That's pretty good. Yeah. So what elements are in there? The melting temperature, what rocks were melted to create that lava. Those are three pretty good things. Number 3, describe the relationship between crust, mantle, lithosphere, asthenosphere, and tectonic plates. Okay, so we can put this all in one sentence in a way. Let's see, how do I put this? All right. Tectonic plates are part of the lithosphere. How do I put this? Hold on. Yeah, tectonic plates are part of the lithosphere, and they float around on top of the asthenosphere. So tectonic plates are part of the lithosphere, and they float around, like they float around on top of the asthenosphere. Tectonic plates are part of the lithosphere, and they float around on top of the asthenosphere. And let's say that I'm going to say, let's see if they tell us. Hold on one second. Depending on where you look, different people have different opinions on where the asthenosphere is. It's usually like right at the boundary of the crust, but I think sometimes they put it as the mantle. They're not even going to show us here. Fine, I don't even look for it. So, and then I would say, well, no. I guess let me look for it. Or maybe should I go back here? Earth's interior. Let's just look at this one. This will tell us for sure what they want. The structure of the Earth, thermal energy. It should be on the next one. Here we go. Earth's crust, lithosphere, Earth's core. Why did they go all the way to the core? Yes, so they're going to say the mantle's in the asthenosphere. So, pull this back up. So we already said tectonic plates are part of the lithosphere, and they float on top of the asthenosphere. The crust is made of the lithosphere and the tectonic plates. The mantle has the asthenosphere in it. So that's your second sentence. The crust is lithosphere and tectonic plates. The mantle has the asthenosphere in it. That's not the whole mantle, but the asthenosphere is in the mantle. So those two sentences should be perfectly fine. Explain how convection can cause tectonic plates to move. Okay, how do I say this? Let's see. So, what is convection? Yeah, it's heat. And what happens with convection and heat?
Rotates.
Yes, but specifically, like the heat does what? What happens to heat? Does it rise or sink? Yeah, hot stuff rises, and so if hot stuff rises, cold stuff's going to do the opposite, right? It's going to sink. Now, can they rise and sink? If I have something rising, can I have something sinking in the exact same spot? No. So something's got to sink somewhere else as I have something rising, and then there's going to be like a cycle, right? It's got to be replaced. And so it's going to come up, it's going to go over, it's going to come down. And so how do I put this into words? Well, it does, but so let's say, what is the question? Explain how convection can cause tectonic plates to move. So I would say in a convection cycle, there is side-to-side motion. And whichever way that motion is moving at the top, your plates are also going to move that way. Which is weird, but I guess that's as descriptive as I can be. So in a convection cycle, you will have side-to-side motion. And whichever way that motion is moving at the top is the direction your plate will move. And there should be a little image of that. So yeah, let me show you all this. Well, I hoped it would get bigger. Can I see it? Full screen. There we go. So you can see the little cycles here, and the arrows aren't the best, but they're coming up in the center, and then they kind of go outward. And so where these arrows are pointing to the left, your plate is going to be moving to the left. Where these arrows are pointing to the right, your plate's going to be pointing to the right. So I don't know. I think that's good. So what did I say? In a convection cycle, there will be side-to-side movement. At the top, whichever direction that side-to-side movement is going, that's the direction your plates will move. Okay, number 5. How can a geologist measure the rate and direction of tectonic plate movement using satellites? We use GPS signals. So we use a GPS to figure out the exact location of that area, that rock or wherever you happen to be standing, that part of the plate. And then you just take measurements over time and see where that point is moving to. So you use GPS signals to take measurements over a period of time, and your measurements should show how fast and in what direction the plate moves. Does that make sense? So use a GPS system, I guess, or what would you call it? A GPS. Use GPS to take multiple measurements over a period of time, and that should show you how fast the plate moves and in what direction it's moving. GPS measurements over time. Number 6, based on elevation measurements over time, we know that the Himalayas are still rising, which I told you all last week. The Himalayas, where India is smashing into Asia, they're still getting taller and taller and taller because India is still smashing into Asia. At the same time, the Appalachian Mountains in the eastern U.S. are getting lower. Explain why this is happening. So 2 parts. The Himalayas are still rising because the Indian plate is still pushing into the Asian plate. So that's part 1. The Himalayas are still rising because the Indian plate is pushing into the Asian plate. Now, why are the Appalachians getting lower? What's happening to the Appalachians to make them get lower and lower and lower? It's not necessarily the plates, it's just erosion. So I would say the Appalachian Mountains don't have any plate tectonics. So the Appalachian Mountains don't have any active plate tectonics, and so they're just being eroded away. So erosion is making them smaller and smaller and smaller. So the Himalayas are rising because Indian plate is pushing into the Asian plate. The Appalachian Mountains don't have any plate tectonics or active plate tectonics anymore. And so erosion is making them get lower and lower and lower. Which we can also see, like the Appalachians, they're mountains, and there's still some mountains there, but they're not anywhere near as tall as like the Rockies, which are a much younger mountain range. They're still nice and tall and have a bunch of peaks. The Appalachians have some mountains, but they're covered in trees. and they're not really like sharp peaks. They're more like big hills, and it's really an old mountain range. And then if you drive up into Oklahoma, you pass through the Wichita Mountains, which are really old mountains and aren't more than just some big hills. It's not even really a mountain range anymore, but they're still there. So, noise. Number 7, magical number 7, lucky number 7. Win the lottery tonight. Never see me again. Distinguish between constructive plate margins and destructive plate margins. It's just that. So what is constructive versus destructive? What does that mean? If I'm constructing something, what am I doing?
Building it.
Yeah, and if I'm destructing something, what am I doing? Destroying it. And that's all it is. Constructive plate margins create new plate. Destructive plate margins destroy or melt old plate. So constructive plate margins create new plate. Destructive plate margins melt and destroy old plate. Creating new, destroying the old. Down with the old people. Rise of the youth. No, it's not even crazy. Okay, explain the 2 types of strike slip faults. They mean continental or oceanic, or they mean left lateral or right lateral. I'm going to assume they're not talking about laterals because they haven't talked about laterals yet. But let me see and make sure that I'm right or wrong very quickly. Can I close this out? Should be an X here. Can I go back? What are my options? Help me, internet. Number 4, and let's just see. This one should be pretty easy, but I just want to see what they want. Here, explore. And are they going to talk about? What are they going to talk about? Come on. Convergent boundaries, divergent boundaries. And then do they go to transform down here? Transform. I guess they're just talking about continental versus oceanic. But that's just 2. Ocean or land. So I'm going to guess, because it's transform, and they had all 3 on the exploration of the transform, that they're talking about left lateral and right lateral. So how does this work? When I'm standing on a transform fault, let me actually use this to show you. A handy dandy manipulative. So I'm standing on a little fault. You're standing over here in the river, right? And I have a strike slip fault. It's not going to go up. It's not going to go down. It's going to go side by side. It's going to move like this. So I have 2 different faults. I have a left lateral and a right lateral. And how this works is you imagine yourself standing on one side of the fault. It doesn't matter which side. They're both going to work exactly the same. Imagine yourself standing on one side of the fault, looking at the other side of the fault. So I'm standing in this river, looking at the river on the other side of the fault. And does it move to the left or does it move to the right? If it moves to the left, it's called a left lateral strike fault. If it moves to the right, it's called a right lateral strike fault. Those are the 2 different types. So explain the 2 different types of strike slip faults. Well, how do I put that? Well, it's shorter and not as many words. Looking at the fault, does the side opposite of me move to the left or to the right? If it's to the left, that's still a lot to say. That's okay. You can write it. So looking at the fault, does the side opposite of me move to the left? If it does, it's a left lateral. Or does it move to the right? If it does, it's a right lateral. I assume that's what they're talking about. That's probably right. So, looking at the fault, does the side opposite of me move to the left? It'll be left lateral. Or does it move to the right? It'll be right lateral. Wonderful, wonderful. Not a very good question there. Yes, I think we talked about this guy. So, who is best known as the father of plate tectonics? Why is he called this? Does anybody remember his name? Yes, Alfred Wegener. Alfred